it's always a hard act to follow after Sovra. I'll never have, as interesting things to say, but at least I hope you'll be all entertained for a little while. Not too long. So what I'll be speaking about today is some work that I've been pursuing with my student, Bogoliubov and postdoc Bogoliubov, and I'll be telling you a little bit about tensionless strings. And this is an outline. I'll start off with an introduction, give you some bit about classical aspects of it, the fun stuff happens when we look at modern versions. I'll briefly mention some applications and wrap up. So why are we interested in tensionless strings? I don't really need to tell this audience this, but anyway, tensionless strings have been studied since Stiles in 1977. This is supposed to probe a limit of string theory at very high energies, and it's also supposed to uncover a sector with large symmetry. So, as we know, string theory has an infinite power of massive particles. In this limit, all of these particles become massless, and we expect that there's going to be the emergence of some high-spin structures out here. So this is also of interest to recent high-spin dualities. Not so recent anymore. There were not Bogoliubov in 2003, Galilean in 2010. And there's been this folklore that about tensionless type 2B strings on ADS plus H5 being equivalent to high-spin gauge theory. Work by Witten and Sunborg in 2001. Some work here has made some more progress in this direction. What we will be focusing on, sort of the aims our initial aims in this venture, we're trying to understand string theory in this outer string regime, and we also wanted to understand if we can make this link between tensionless strings and high spins more concrete. And sort of our take on this was that we wanted to view things from the point of view of the worldsheet. What we were saying that, central to understanding string theory had been the fact that we had, two-dimensional conformal field theory on the worldsheet. What was happening in this case is, in this particular limit, that was something that seemed to be lacking. And what we want to make a claim at is that we have been able to look at similar organizing principle out here, and we're just starting to see how the building blocks of this can be put in place.
And sorry, I'm sure you're defining it, but tensionless means energy is much bigger than the string tension, or what exactly does that
so
mean?
I'm going to take alpha prime out to infinity essentially.
So that's a dimension for parameters.
That is right. That is right. So I'm going to be working in flat space. So what I will be doing is that I'll have an observer scale. In some sense, you can think of this as having the string scale being much larger compared to the Planck scale. So that's.
You mean G string going to infinity? Is that? Normally, your string
energy is larger than this, right? Larger
than
string scale. But you want to still keep Planck scale much.
So let's say that for the things that I'll have, this is not going to be so important right away. But I will have an observer. As you said, this is. If you take something to infinity, it has to be a dimensionless number. So I'm going to define something that I hold fixed called C prime essentially. Instead of an alpha prime. So that essentially means that the observer has a scale. Since we're doing things in flat space, we do not have any other intrinsic scale to it. If we had done played the same game in ADS, ADS radius would have played a role there. But we would introduce another scale which we maybe call the observer scale.
Could I just ask you the following? Are you taking energies in string units to go to infinity, while keeping the string tension say smaller than the Planck scale? Is that the limit you're interested in?
We would be looking at sort of the high energy states. We would like to, from the point of view of the worldsheet, at the end of the day build up to something which reproduces gross mandate and things like that. So it is a high energy limit, yes. So this is, I mean, so I just list out what we are trying to do. What we will be seeing is that there is a re-emergence of the stuff that I mentioned earlier regarding Galilean symmetries on the worldsheet now. What we will find out is that, I mean, we'll have two distinct ways of going about it. One would be intrinsic in the sense that I'll show you how to get an action for these things, and everything we can derive from the action we will call intrinsic. And for similar things, we will also get things from the limit of the usual relativistic string as well. And we'll see that in the classical case, everything matches, and it's this nice way of going about. In the when we look to quantize the theory, however, there are important differences which we seem to creep up. And then here this hints to new physics, and we just mentioned a little bit about some interesting connections to strings. I mean, here the hydron base connection. All right, so I said I'll entertain you, so I'll have to put in some figures. So what we're going to do is we're going to take limits. So this is a very, very simple example of how we take a limit. So we have little prince on its planet, and little prince is a very strong, I mean, very powerful little guy. So what is going to happen? So we know the equations for the sphere, we know its infinitesimal generators, and we know the algebra of the infinitesimal generators. Little prince wants to actually take the radius of the sphere out to infinity. So what does he do? He wants to also try and understand things from the point of view of the algebra. So very good. What we do is, he sits at the North Pole and then takes this radius out to infinity. What happens here is the x1, 1, 2 generator stays the same, and the other ones which have this explicit factor of r in them, what we have to do is we have to divide these out by another factor of 1 over r, so that at the end of the day, these generators don't go out. So we find that, I mean, you get the usual algebra, obviously, and the point that I want to make out here is that once we take the limit, if we find something blowing up, it's mainly, essentially, that we have not defined things properly. We need to multiply it with appropriate factors of r and so on, and then things become all right. This will be extensively used in what we do again, but yeah, this is sort of a carbon way of trying to see how we take limits. So this is going to be useful. So quickly, what do we want to do? So this is actually work from 3 by Isborg, Lindstrom, Sundborg, and and if you start off with the Nabu-Goto action, so we have a factor of 3 which sits outside. So it's obviously not good to try and take the tension out to 0. This is just going to make our action equal to 0. So what we do is we switch to the Hamiltonian. We define generalized momenta, and we have these constraints on the string. I mean, obviously, since we have diffeomorphism invariance on the worldsheet, the canonical Hamiltonian will be equal to 0. So what we have is Lagrange multipliers. So the total Hamiltonian will be just Lagrange multipliers multiplying the constraints. So this is what our Hamiltonian is. Now what we do is we integrate out the momenta. And once we do that, what we see that we have an action where the tension has moved from being in front to being a term inside out. If we rewrite this in the familiar Weyl-invariant form, so the model of action now looks like this, where G upper alpha beta is defined by this guy. Now you see that when we take T out to 0, what happens is this particular metric determinant. This term drops off. So this is, rho squared minus rho squared. So the determinant is equal to 0. The metric becomes degenerate. So what we'd like to do is we'd like to replace this degenerate metric density by these vector densities V alpha. And then the action that we can write down in the tensionless limit is given in terms of these V alphas. So we could take 5 as the starting point of our theory of these tensionless strings, and we could construct everything out. So when we do that, this is what we call the intrinsic way of doing things. So that's one.
So this is now it's a degenerate worldsheet.
It's a worldsheet which has a very degenerate metric on it. So that's going to be the feature of it, which is going to come back.
So this lambda and rho were Lagrange multipliers?
Yes, that's right.
So now they are also integration variables. So you have the x, what I mean as a functional integral. So now the quantum theory would have functional integrals over the x's and the lambda and the rho.
Yeah, so what we will do is we will just think of this in terms of the v's and the x's. So
okay, v is like dynamically variable.
Yeah,
X is
that's right. So what I said was that what we have done is we have looked at the usual tensile string theory. We have gone to the tensionless case, and what I define as a fundamentally tensionless object. That in theory will be something, if you find your corresponding favorite things in your tensionless theory, what we will be able to show is that you will also take some limits to go from here via this route. And in the classical theory, we will show that these two land you up in the same thing. So that's the next part of it. So what we want to understand are symmetries. So what happens, what we do in the usual case, so there is the tensionless action is invariant under worldsheet diffeomorphisms again. And what you can do is you have to fix a gauge. And there is an equivalent of a conformal gauge which you can fix, and these A's can be fixed to 0. As we know very well, in the usual string theory, there's some residual gauge symmetry. Even after we fix the conformal gauge, this is this two properties of your Bogoliubov algebra. This is what gives you the 2D CFT, and this is what is fundamental to trying to understand what string theory is. So what is going to happen is in the tensionless case, again, there's going to be a similar residual symmetry algebra which is left over after gauge fix. So let's see what this is. So if you are looking at worldsheet diffeomorphisms, so these V's are some vector densities. So this is going to change like the following. Now we have a gauge which is V0. So what we can do is we can plug this back, and then we will get equations for these E alphas. And what we can show is that this E alpha, the form of these E alphas, which leaves this particular V0 gauge invariant, is of a form like this. So you see that there's only a linear dependence in the tau variable, and there are sigmas which are floating. Very good.
So sorry, if you can just go back to the action of the tensionless string.
Yeah.
So are we going to be summing over V alpha? Just as we start by summing, when we write the worldsheet action, then there's the worldsheet metric, and we at least first to begin with have to sum over it, then we say, oh, this conformal and resolve that.
Yeah.
Is there going to be similarly a sum over on V alpha, or is it?
Sum over in the sense that so what we had in the usual string theory. So this is the equivalent of the G alphas and G alpha betas, right? So I mean, what you're doing is that, so that we had, I mean, in the conformal case, that is fixed to a fixed flat band on the eta alpha.
I mean, not really. There, what you first say is you can go to conformal,
That is right.
then you
That
do
is
sum over all metrics, but because the theory is conformally invariant, that sum over all metrics is just some universal factor that you take out.
Yeah, so I mean, you can do, given this action, so one thing that you can actually can obviously see is that what symmetries is invariant. So I'm saying that the V alphas also have a diffeomorphism invariance, which leaves this metric invariant. So we need to fix V alphas, I mean, of a certain form.
Right. I'm just asking, what is the theory? This is the action, and the variables are xm and V alpha.
And yes.
You're going to be summing over V alphas also in the path integral.
Yeah, if you're thinking of it, I mean, as a path integral, yes, always. Yes. So if you choose a gauge which is V0, I mean for this V alpha which is V0, then these E alphas, I mean these worldsheet diffeomorphisms, the allowed ones that leaves this gauge invariant are given on this one. So now you are in a situation to find out what exactly the algebra of the guys is, and so we can do a Fourier analysis out here, and we can find out what we can decompose f and g in terms of Fourier modes, and we can find out what the generator of this algebra is. And turns out that if you do this in the same way that you had brought the two copies of your Virasoro algebra previously, this is the algebra that you end up with. I have more to say about sample terms, but you see that there is one copy of your Virasoro algebra out here. There are some mixed terms out here, and this is something that we had looked at earlier. So this is called the two-dimensional conformal algebra. It arose in various contexts earlier, as in residual field theories, non-relative limits of ADS-CFT, and also interestingly, the same thing is called the BMS3 algebra again. So this is also has been important for some of our excursions in holography of
the aim generates what? Like L is what I can think of in the normal sense. The aim is the generator for like it's.
So this is, I mean, these are, I mean, abelian. This is sort of an abelian subalgebra, you could say. So this is something that happens. If you're thinking about things in terms of, so this, as I said, also arises as symmetries in flat space in 3 dimensions. So this is something, if you're looking to go out to null infinity, this is the asymptotic symmetry algebra of 3-dimensional flat space. There, these M's are what are known as super translations. So these are translations on strike plus which depend not only on the null direction, but also on the angles at the null direction. So this is the same thing that is sort of arising.
L bars are gone. There are no L bars.
There are no L bars.
I see. But I would have thought that the initial action still had a left-right splitting at least. You know, if you look at B alpha, B beta, del alpha, isn't there still a separation into holomorphic and anti-holomorphic?
No, that is the thing actually. So the theme will be that there is actually mixing. So there's been this thing about I mean open the intentionless strings and the tensionless limit of string theory. The distinction between open strings and closed strings are sort of blurred out. We'll see why that is.
So just a question in terms of the algebra, isn't it a linear combination of the L's and the M's so that I get an L and an L bar algebra?
No, you will. What you'll see, what I just go on to is that this algebra can be reproduced as a linear combination of L and L bar, but I mean it's a limit. So it's a singular limit of these algebras. It's a contraction in the sense of the algebra.
So one more question. This gauge that you fix, in that it now becomes like a sum of particles, is that right? I mean, if you're taking V alpha is equal to V comma 0, so So now you
So-
will have only x dot square
That is
in Lagrangian and no del x del
That's-
sigma. I mean there is no linking term. So
That
it's
is-
just
that
the
is-
sum of the beats.
that is right in a way, but there's going to be another constraint as well. There's going to be, so we
But all
just get to
constraints
that.
are taken care of by the Lagrangian multiplier.
That is right. So we'll get, two things out there actually. So let me just get to that. There's going to be something.
There's a weak equation of motion.
That's right. That's
The
right.
spatial part.
That's right.
I see.
Arjun,
Yeah.
a question.
Yeah. Sure.
When you say that C1 equal to C0,
Yeah.
this is a statement above the x, just the matter x. If you calculate its contribution to this set of charge is 0 or
Okay. Right now, I've not said much about central terms, except for the fact that these guys who I'm quoting right now find that to be equal to 0. But you're right. I've not included any matter things into into my formalism yet.
but what are they finding? What is the actual exact calculation they did? Like,
you're asking what is it that these guys did?
yes.
Okay. So there's actually not only these guys. There are a number of people who have been looking at particular normal ordering and so on. So it's not one group actually. So the literature in this case is a little not so clear, but they do some BRST analysis as well.
For this x, for this factor action.
Yes. So what I'm trying to say is that there are a number of different people who come at this thing from different angles, and some of them find that these C's are not non-zero. Some of them find them as zero. So it's a little bit of a mess out here. So what I'll be saying is that the guys Isberg et al. What they find as CL and CM equal to 0 is something that is natural from the limit. So I'll show you that in a little bit, probably next slide. So what we want to understand is precisely what Surat was asking, is that how do these symmetries arise as a limit? So again, so if you are looking at the tensile string in the conformal case, then you have two copies of your Virasoro algebra, and you have a C and a C bar. Now as I didn't stress this enough at the beginning, but we're going to be looking at closed strings, closed bosonic strings to start off with, and so in that case, obviously these symmetries are best expressed on the cylinder, and let's say L and L bar are the things that we do, and these are the vector fields that generate the Witt algebra. Now the tensionless limit is the limit where the length of the string becomes infinite. The string becomes long and floppy in this limit. So you could think of this as a limit where sigma actually goes out to infinity. Now we are dealing with closed strings instead of trying to put sigma out to infinity. Since you want to identify the ends of the string, it's better to take sigma to sigma and tau to epsilon tau. And if you do this, what you can see is that you can define linear combinations L and N, which are L minus L bar minus N and an epsilon times Ln plus L bar minus N. And if you do this and if you take the limit, then what you can show is that and use Ln and expressions of Ln and L bar in here. So you can see that Ln and Mn come out to be a form like 13, and this is precisely the form that we had found earlier.
So this C goes to no. So what happens to C in this limit?
The center charge?
Yes.
Yeah, so that's the next slide. So Cl becomes C minus C bar, and Cn becomes C plus C by N. So the epsilon is actually
So
opposite.
that goes to infinity.
So this actually goes to 0. So this should be upstairs. I'm sorry.
So each C and C bar goes to infinity, right? The left and right central charges of the original CFT go to infinity.
If you want to keep a non-zero Cm, you need to put C and C bar both go into infinity. So the thing that I was saying is that now,
but you don't have freedom over C and C bar, no? Aren't they fixed?
True. That is precisely what I want to come to, in the sense that if you are looking at tensionless strings as a limit of a consistent string theory, if you want to look at this as a subsector, then your C and C bar are fixed. If you want a theory to have no diffeomorphism anomaly, then your C is equal to C bar, which puts your CL equal to 0. And C and C bar are also, I mean, this theory also has, I mean, a finite number of worldsheet fields.
Exactly 26, right?
That's right. So if that is the case, then C and C bar can't scale as 1 by epsilon. So Cm also has to be equal to 0. Okay. So this is what is in keeping with the earlier I mean, Isborg etc. analysis, that CL and Cm I have to have.
But I don't even understand the scaling, because there's no deformation of the algebra that's possible. It's just an algebra. There's no scaling in it.
There's
When you say you scale, take a limit of the algebra.
Yeah.
It's a limit where you vary the central charge, and then you get this new algebra which has this new CL and Cm. But if you have a critical string, there's no varying.
No. What I'm saying is this is a limit where you don't need to vary CL and Cm. That is fixed, right? So we are trying to understand. So at least part A is that we're trying to understand this particular thing as a consistent subsector inside string theory, which has already been defined. So your C and C bar are given to you. Now you want to go to the tensionless limit of that theory.
But from the algebraic point of view, I don't understand. What does it mean to take a limit of the algebra? There's nothing you can vary in the algebra.
No, this is a contraction of the algebra, right?
But I thought usually when you do this, like when you try to take, this flat space holography kind
Yeah.
of, you vary the central charge. Which you can do there. So you take a limit of the central charge and
Not really, actually. So if you are looking at say the limit of ADS going out to flat space, in that case your C and C bar are fixed in terms of the ADS radius. I mean it's 3L over 2G.
So you change that.
Yeah, I mean you. So if you had these things fixed, I mean, so what I'm trying to say is that if you were to look at one particular theory, and you try to take these singular space-time limits in them, in that case, so here Cm would essentially be 0 if you do not have your extremely large central terms to start off.
No, but I have a question even before that.
Yeah.
What is it in terms of the algebra in the Hilbert space?
Yeah.
I don't even understand what this means, because you could say either that you're looking at a subset, right? You see that, right? So you have a fixed algebra.
That's right.
It's an algebra, and there's nothing you can do to deform it, because it has a fixed value of C, and the algebra is completely controlled by C.
No, the algebra is not the same anymore, right? So it's not a change of basis out here. It's it is a change of basis, but it's a singular change of basis.
Yeah, let me perhaps rephrase what Subrat is saying.
Yeah.
So in case of the n equals 4 super angles, your central charge goes as n squared.
That's
So
right.
there is an n there.
That's right.
So there is a meaning to taking that n to infinity.
Mm-hmm.
And so here, if you start with some worldsheet theory with C equal to 26,
Yeah.
CL and CR equal to 26.
Mhm.
So that's frozen. That's sort of set in stone.
Okay.
Unless you were making, where is the counterpart of that n?
I mean, then the algebra is
Which you
the
could take.
algebra.
Is that?
Yeah, that's the question. The algebra is just the algebra. It's
Really sorry, but could you back up?
Sure.
Where did you introduce epsilon again? Just 1 minute.
Okay.
Okay, so that is just a definition of Mn.
That's right.
Okay, and so you start with L and L bar. You
Yes.
find your n with epsilon.
Yeah.
Okay, and then just go to the next slide again. Okay, and then your point is that if you wanted the seeds to scale like this, then you would get the other side. Okay.
Otherwise, it's just the same algebra. No? It's a Virasol algebra where you make some basis to make it look.
No, it's not. That is my point is So what happens is, if you let's say we don't look at central terms at all. So we have ln mn as n minus m as n plus m. And we have so let's just rewrite it in the way we have done. So this ln mn will give you the same thing. So you will have ln mn gives you again. I mean, so far you're right. What happens now is that you get an epsilon squared which sits here, and you get this.
You didn't put any central charges in.
Yeah, I'm just saying what happens if you do not put any central charge.
So this algebra right now.
This is, I mean, as you're saying, exactly the same thing.
So far with the finite value of epsilon is
Exactly the same. There is just a change of basis out here which I'm. All I'm trying to say is, when you take the singular limit of epsilon going to 0, then this term drops off, and it's no longer two copies of your weight algebra.
So why did you get epsilon the term above?
Because there's an m here and an n here.
Oh, m here.
Okay. So this, even without the central terms, is something which is not the same. So the thing that I'm trying to say is that from the point of view of consistent string theory, if you are trying to go to a sector which is the tensionless sector of this consistent theory, it makes sense that the central terms CL and CM are both seen. Now, just to make sure that you guys, also feel happy about life. If this were a theory on its own, it could have had central terms CL and CM. So this is an analysis that has to be done, which we are trying to do. And this, this is going to depend on some specifics like what the particular operator and so on and so on. So at the end of the day, option 1, this limit does not generate anything extra, in the sense that this tensionless strings, as the limit of usual string theory, is consistent in any dimensions. This is good in a way, because we do not want to start off with a theory and take a limit, go on to another, a sector of the theory, and then find out that that particular sector was valid in some other dimensions, right? If it was d equal to 26, it is fine. If it's not going to give us something extra, it is also reasonably. So this was at least from the point of view of the limit.
Marshall constraint. That's the Marshall constraint that you have in loud primaries that you're going to look at. What happened to that here? In this tensionless limit?
So
constraint at L0 minus 1, L0 bar minus 1 is 0.
Yeah, okay, so the Marshall, so what we're going to do is we're going to look at what the constraints are for, our theory, that's next up. And we have, as I said, there's so we had written down the classical version, and we have the constraints. We're going to impose it on the Hilbert space. That's what we're going to do next. So yeah.
Yeah. So if you rather than trying to do it just in a non-gauge fixed theory,
Yeah.
let's say you also add the DC code.
Okay.
And then do the scaling.
Okay.
And we know that after you add the DC code, the total theory does have a central charge 0, even in the tension string.
Okay.
Like, that's a very variable.
Yeah.
The 26 of the X has the
Right.
26 of the BC.
Right.
So then then you would expect to get the C 0 even after you contract.
True. Yes.
But then the question is how do you scale the DC system? Whether your DC system also you can do this B trick.
So this is a thing that I've not looked at, but I think one should be as you're saying there should be a way to try and scale this as well, and the central charge of the system will not be there in the limit, but it's going to be not your usual BC ghost system, but a contracted version of that.
You don't have
It is understood what is a contracted version of the BC system.
It is not. It is not understood. This is something that we wish to be looking at in a few days' time, essentially. But this is something that should be done, and that surely can be done as well. So things, yeah.
Why is it not? Is it difficult?
No, it is not. It is just that it has not been looked at in this way before, essentially. That's all. So people have recently, in the context of flat holography in 3 dimensions, looked at limits of Liouville theory. So one can do that. So similarly, I think you should be able to also scale the BC ghost system and try and get results.
So another way to do it is, of course, also to go to the light cone gauge, in which case you don't have to worry about the BC system.
No, the thing is, I would not like to go to a light cone gauge. I'll try and so what we are trying to do is trying to get rid of what's happening in space time, for example. So the light cone would explicitly take that into account, right? So we are doing a very singular limit on the string worldsheet. So we don't really know what happens to the space time. So that is why I'm a bit reluctant to try and frame things in terms of the light cone. So that's one reason. So a lot of the earlier literature had been looking at things from the point of view of the light cone. This is one thing that I really want to avoid, because I do not want to say that these things propagate in flat space and just do things from there, essentially, because there is information there which might not be true. This is a very singular limit, right? It might do things to your background geometry.
But on the other hand, you have a V alpha, a particular vector.
That's right.
So it is it is polynomial to there's a vector, so you can use it to try to probably you need a vector in the space time. Sorry, I think.
Yeah. So the thing that I'm trying to say is just let's try and focus on the worldsheet, because we probably would be able to understand things better from the worldsheet. And one of the reasons why not that much of progress has been done is people have been looking at the space-time and trying to look at the light cone, and lots of mess out there, essentially. So this is maybe I don't know yet, but it seems to be a way that you can actually construct analogs of things that we have in usual string theory and push forward. So yeah. So yeah.
Change of basis in the algebra.
Yep.
Some of the change of basis shouldn't give you anything. You shouldn't get anything.
This is singular change of basis, so this is not a change of basis per se.
Singular change of basis.
Yes.
What is it? How does it gain you something to do the singular change of basis?
I'm just saying that the algebra will change. If the algebra as you see things obviously will change, and it's sort of like trying to go from, say, Lorentz to so from a relativistic onto a non-relativistic system. It's not a question of gaining something. What I'm trying to say is that you might be able to gain intuition of this limit by actually doing things, taking the limit precisely. So we know some things about the we know a lot about the tensile case, which seems that we do not know as much about the tensionless case. I'm just saying try and use techniques we already know and make this limit precise, and then understand what was it.
Just one more.
Yeah.
Naively, if I wanted to take this tensionless case, which was taking states which had energy much larger than the string scale, I would have focused on the same constraint algebra, somehow tried to focus on states where there's center of mass k squared.
You need to give me a little more time about this, because so the real fun is when I'm trying to quantize the theory. So there are things that I do not understand out there, so that it will be good to have your feedback. So what do we usually do? So we the generators of the Virasoro algebra are modes of the energy momentum tensor. What we usually do to get the spectrum of the tensile theory is that we quantize the worldsheet theory as a theory of free scalars, and we impose a vanishing of the equation of the motion of the metric on this, And so the physical states vanish under the action of these modes of the energy momentum tensor. And this you also have to decouple the negative norm states from the Hilbert space and so on. So what we can do on a purely algebraic level is try and understand what the energy momentum tensor of the underlying algebra is. And that's again reasonably simple to do. You can take linear combinations. Just remember to just put your use expressions of the energy momentum tensor on the cylinder, and you can take limits and you can get nice looking expressions. And then the constraints of the tensionless string are these two T1 and T2 vanishing. This needs to be imposed on the Hilbert space of states found by quantizing the theory to generate what is the physical state. So this, in operator language, is handled between two states, and then
So just to understand, here you took the equation of motion of the full 2D metric, all components, right? And then you put the metric to be digital. I'm just trying to understand. Usually you get these equations for the Bogoliubov from the metric equation.
Yeah, we will be doing that. We'll be trying to do things, as I'm saying, in two separate ways. In one where we'll be starting off with the action that I gave you, and doing things just from the action. We write equations of motion, then right. So that's just next up. And the other is you can take the mode expansions as they are and take limits and see that everything fits in very well. So that's what I plan to do next.
Here what you're doing is, I'm just trying to understand, because usually you set the metric to be flat up to the conformal factor, which goes away, and then you get the equation.
That's right.
And here you're doing that, but
here we're going to set the VA that we got, this vector density, to be V0. So that is the choice. That's
what I'm wondering. If you just varied the VA, you wouldn't get all the equations of motion that you would have got by varying the metric.
You would.
Because the VA is a very degenerate limit of the metric, right?
Yeah. So what we want to look at. So the replacement was this.
Right. So what I'm saying is, if you're very G alpha beta, you have got T alpha beta is 0.
That's right.
Whereas if you restrict yourself to a degenerate metric as parameterized by V alpha, and you only vary V alpha, then I would have thought you get a restricted class of.
That is right, but that is what we want, right? So we want to be looking at the limit. So the equations of motion will not be those which are generated by general G alpha beta. This is just trying to take into account the fact that G alpha beta is actually a degenerate metric. So
what you're saying is you start from the left hand side by varying G alpha beta, you get your equations, then you take the limit, and you get some set of equations, or you start from the right hand side and vary V alpha and you get equations.
And we will be able to show you that these are the same. So let me just do that. So what we want to do is intrinsic analysis. So we have fixed the gauge as D0, and the equations of motion in this case just simplify to x double dot equal to 0. So we expand out in modes. We'll have linear terms, and we'll have stuff like this. We also want to concentrate on the closed strings. So this A naught term drops off. So your solution is now x mu, this term, and this term. So
now just to understand, the equation is x mu double dot equal to 0 by varying V.
So this one is the equations of motion. So this is varying x's, and the constraints that you'll get will be the thing which give you x. So you get x dot squared equal to 0 and x dot x prime equal to 0.
Thank you.
So we plug these two in. We use our modes.
When you vary V, I thought there's just one factor of V initially. Oh, I see. So that factor of V you said to be V0.
That's right.
I see. How do you know this doesn't depend on the gauge? It somehow, quantum mechanically, how do you know you don't get an anomaly when you do this?
So I mean, so the intuition in some sense is, you know, G alpha beta. So this is what? This is, yeah, something here. So you have 1, minus 1 and 1. So what you're doing is you choose V alpha as having V0. So in this limit, this is as you saw a limit where, so okay, in terms of the space-time thing, what you can do is this can be looked upon as an ultra-relativistic limit. So this term goes to 0.
No, I understand that you get this. Actually, maybe I should let you go on because I'm concerned about the fact that the critical dimension and so on came from the fact that there shouldn't be an anomaly when you quantize constraint. So you're saying there's no analog of that constraint.
Here he is just deriving the equations of motion from the metric.
Yes. So far,
Yeah.
just
So far, I've not. I mean, yeah, I've been spoken about anything. So I'm just trying to build up just the basic bricks, right?
So then, as you say, those are operator equations, and when you
Exactly.
define the operators, somehow
Exactly.
you might have to-
Exactly. Those things could be appeared, but we've not got there. So the constraints are x not equal to 0 and x dot x prime equal to 0. And if you do this, if we define ln's in terms of a's and b's and mn's in terms of 2b's, then you can see that the modes that we have reproduced that were used in the last slide, they again show up out here. So these are, these were previously obtained from purely algebraic point of view. Now we can use the mode expansions here to relate. Very good.
in tau.
Yeah. So what happened is, so what we did out here is we looked at T1 and T2. So these were combinations like this. So you had an n tau which came in here. So this is a signature of the fact that, you know, these super translations always are sort of linear. Okay, very good.
So these constraints can be thought of as the ones generating the residual gauge transformations in this gauge, or how are you viewing these constraints?
So these things. So this guy is so one. I mean, as we will see, is going to lead on to a sort of level matching sort of thing out here.
No, but how are you getting that one? I can see x dot square equal to 0 coming from just the V equation of motion. Right?
Yeah. So you
and
get.
other
I mean,
one, I'm just asking about the other one. X dot.
yeah. So
dot
you
x
should
prime.
you should just get this from the. So there will be an equation. So did I write down the equation?
Presumably that generates the M algebra, is it? That.
I think the equation from here will have one index. You see, because
Yeah, so-
beta into del
So you
beta del
have something
del
like a
phi.
del
So
mu
you
of
have two
No, but if I'm working in that gauge, then I have to look at the residual gauge transformations, and I have to see what are the constraints related
So-
to that residual gauge.
So you have your action. You write down your equations of motion.
Yeah.
And what you do is that in those equations of motion, the V alpha equations of motion generate your two constraints. And what I'm saying is that in this particular gauge, in the V0 gauge, this actually just reduces to these equations. So that gives you, I think what the equation is something like gamma
I mean,
alpha.
just like in the conformal gauge, in the
Yeah.
usual thing,
Yeah.
I can think of the TZZ equal to 0 and TZ bar equal to 0
That's right.
as the ones generating the residual
Yes,
gauge.
I mean these again will do the same thing. So it's an equivalent of that. It's a T1 equal to 0 and a T2 equal to 0. These would again generate your residual gauge transformations as well. Okay, moving on again. So we can look at the algebra of these modes, and you see that AA with the BB is 0, but the AB is non-zero. So the point to note out here is that this is not the algebra of harmonic oscillators modes, and we'll have a little more to say about this later. Not
So
to say
what are the A's? You just go back.
Yeah.
So far it's L and the A's are here. Okay.
Yeah, so the A's are here. Okay, so you can use this to now look at, as you were saying, these A's and B's are going to be the modes that generate this symmetry algebraic. Right? So depending on how much time I have. Okay, let's just do this. So now we look at the usual string mode expansion. You write it in terms of alphas and alpha tildes, and we look at the limit where tau goes to epsilon, tau sigma goes to sigma. And here is the scale that you were referring to earlier, Sandeep. We wanted to have a dimension-less number going to 0, so we have introduced this scale C prime. And it's to be interpreted as some observer scale. So you look, take your mode expansion, put your factors of epsilon in, take the limit, and you would see that if you really find A and B in this particular way, then you again end up with the limit that I spoke earlier. Okay. Very good, so far so good, and things are matching. And now we want to understand how to address the quantum aspects of what we have done so far. So we are going to be separating two things out here. One is, as I said earlier, we would be looking first at quantum tensionless strings as a limit, as obtained from the tensile theory. So this is so we already have have a Hilbert space, but the constraints that we have changed. So we are to impose these different constraints on the existing Hilbert space. So as I said, the tensionless Hilbert space is one of them from the tensile theory. The metric degenerates, so the constraints on the system will change. So we impose this on the Hilbert space. So what happens is that the physical Hilbert space is built out of zero alpha oscillators, and these are things. So you at a generic level, this is the state, and what you get is very trivial at the end of the day. So you look at your mass square operator. This is what you get. You impose it, and everything goes to 0 as you expect. So
Mass square is 0.
yeah, so the mass square is 0 as you would have expected naively as well, right? If you had just taken your usual mass square formula and naively put alpha prime goes to infinity out there, you get all of these masses going to 0. You just recover that. There's nothing profound happening.
So the original CFT you started with was not unitary. So I'm worried about why you get unitary theory in space-time. Are you going to say
Why was the theory not unitary?
Zero mode, right? I mean, the
What?
original worldsheet CFT is not a unitary CFT.
Okay.
How do you know you're going to get a unitary theory in space-time with these things? Are you going to say something about that?
I'm not going to be speaking much about space-time, but we will see that a few weird things are happening in the next slide when I'm looking at the purely tensionless theory as a fundamental theory. But so as Loga was saying earlier, it's proper to add the BC Ghost system in and then look at the whole system and then take the limit. So that's the best way to go about it. But I'm again sort of trying to build the basics here again. All I'm trying to say is that this analysis that we did, at least in this case, seems to be leading us to answers which we would have trivially explained.
Anyway, not all states are allowed. Only states to satisfy the constraints are allowed. So the constraints in terms of these oscillators will make some particular combination of oscillators.
Yes. Now,
at least this makes good sense to me. At least the way I interpret it is that okay, it's the original string spectrum,
yeah.
but you're really interested in energies much bigger than the strings.
That's right.
That's right. So
right.
in that way, the masses you can set to 0 because
yeah. So it's not. It's not something that you wouldn't have expected. This would have been the first thing that you would have expected. It's good that it's come out, but it's not very exciting.
But the thing that confused me about that way of looking at things is it would have been very nice if you could take the original algebra, the Virasur algebra, and show somehow that acting on a subset of the Hilbert space, there's a way to understand that turns into this algebra of the L's and N's. That's the link that's not clear to me. So there's a subset of the Hilbert space which corresponds to masses much higher than the string scale. So somehow maybe acting on that subsector, it's possible to approximate this algebra by the algebra of the L's and the N's.
Maybe.
What's not
Yeah.
Maybe it's not.
Such as by looking at very large formal modules.
Maybe, right. That's right.
So we'll so now what I want to say is that suppose we didn't have this idea. Suppose you are handled this string, tensionless string action to begin with. You didn't know it came from any limit or anything. So those were your fundamental objects. How are you going to go about trying to quantize that theory? Now, as I said earlier, just a little earlier, the A's and B's that we wrote down do not satisfy a harmonic oscillator basis. So let us shift to something which is a harmonic oscillator basis. We're going to call these guys C's and C tildes. So the algebra of C's and C tildes are the things that we want. Now is the fun part. If you want to relate C's with alphas and beta, with alphas and alpha tildes, these C's actually become linear combinations of creation and annihilation operators. Okay? So, what happens is that the tensionless ground state is no longer the same as the tensile ground state that we had earlier. So, if you want to understand from this point of view, then C's and C tildes acting on this new ground state should be equal to 0. But that is clearly not the same as, alphas acting on the other ground state being equal to 0. So these are Bogoliubov transformations acting on the worldsheet now. Okay? And so you can relate the two backward. And in that case, one vacuum is going to be a squeezed state in terms of the other vacuum.
Okay, what is theta?
Okay, so okay, all right. So these are not very relevant. This was just written in terms of familiar looking form. So all I did was so there was a relation between A's and B's and alphas. So redefining so that it's a harmonic oscillator basis. You can write it in a form like this, where this B pluses and B minuses are alpha form like this. So this.
Arjun?
Yeah.
Just a question. This. So the physics of it is that what we would expect. We would expect these high strings to go down,
Yeah.
become massless.
Yeah.
So that presumably there's kind of a inverse Higgs mechanism happening. Which means that you should get a bunch of bosons and gauge fields. Right?
Okay.
Isn't that?
So that is what I was saying when we were looking at the looking at the theory as a limit. So I'm trying to distinguish now between a theory that I get as a subsector and a theory where my fundamental objects are my tensionless strings, where I do not have it. Yeah.
I'm just asking a question. Regarding this change of the vacuum. So
yeah.
Really, it seems to me that physically what you should be doing is that you should be identifying the longitudinal null states of these highest-string gauge fields or whatever. First of all, you should identify highest-string gauge fields.
So
other states, and then other states in the homology which come about which these gauge fields can eat.
Look at the thing that I'm trying to say is that since this is a very singular limit, let us not think of things in terms of the space-time at all. So I'm not going to be trying to speak about higher strings at all right now. I'm just interested in a theory which has an action which I showed you, and if I quantize that theory, this is what I should naively expect. So I'm just going to try and see what this gives me instead of trying to also play on my earlier intuition that this should give me a higher spin and so on. Instead of trying to do that, let me just come from the perspective of purely the worldsheet and try and see what I get. So that's my so it may be related to that, but as you'll see right now, it has more interesting stuff hidden in it. It seems to me at least. Yeah, but you have a point. Yeah.
Just back to
yeah.
first question, BC goes. So if you
Yeah.
had a BC goes and if you had a DRST charge and so on.
Yes.
Seems to me that the new vacuum
Yeah.
is not here because it would be annihilated by the DRST charge. You have to be careful in doing this kind of Bogoliubov transformations.
True.
As a gauging basis, right? Because it's not.
Yes.
It's in a proper DRST analysis, it's not clear that you can.
So what I'm saying is that if you were to do quantum BIST analysis, which is inherently in this tensile string, tensionless strings, which are fundamental objects. You would have to think of them in a way which is not something which comes from the limit, but you have to treat it independently. I don't know yet how to do that. But all I'm trying to say is that here it seems that the natural vacuum that you get with these C oscillators is something which is going to be a squeeze state in terms of the alpha oscillators. So this is sort of like a high energy state, extreme high energy state.
So the reason for introducing C oscillators was that the A oscillators and the B oscillator commuted, right? Or the Poisson matrix vanished. Right?
That's true.
I mean, which usually is not true. That there was this whole bunch of oscillators in the tensile string theory.
Yeah.
Which all the oscillators just became degenerate.
No, hold on. The reason why a new set of oscillators was introduced in the first place was because the alpha oscillators. So we had this mode expansions, right? There we had some A's and B's. Let me just show that to you.
Yeah. So the A's.
So we had stuff like this. Okay. You can't see that yet. This is equation 23.
Here's the slide.
Yeah. So the A's and B's are response to the difference of the oscillators.
That is right. So all I'm trying to say is that this particular guy. So the reason why I've switched to the C oscillators is because these A's and B's do not have a harmonic oscillator basis. But the fact that the vacuum will not be the same also stays true, right?
No, but Arjun, the reason the A and B oscillators degenerate, it seems to me that from a string theory viewpoint, has a physical interpretation that there are new null states, which is what you would expect when you have.
I agree that there could be new null states. I'm not sure if there will be, but there is a possibility that there could be new null states, and these null states could be related to high spin structures. But
you have massless high spin excitations, right? So you should have new null states.
Yeah, sure.
So the longitudinal guys should be a null state of the high spin.
Yeah, but that is an analysis that you need to do. It's an expectation, but it needs to be borne out by some some math at the end of the day.
Yeah. So what I'm saying is that the reason there's a zero is there's a null state 0, and so it seems to be confusing because you're trying to get rid of the 0 by going to another basis. So I'm uncomfortable that because the physical state. I understand that you don't want to think about space-time, but from a space-time point of view, there's a reason that the oscillators degenerate.
True. I get what you're saying, but I'm sort of trying to take a very naive way to do this right now, and I'm trying to see what I get on my fix, and it's sort of a large body of work in progress where we also need to understand what the hell is happening to space-time and so on and so forth. But let me just show you where we have gone so far, and there are a few more provocative remarks which are coming up. So let's see how you react to those. So the thing that I was trying to say is that the zero C vacuum, if you agree that the C oscillators are the right oscillators in which I want to view this this fundamentally tensionless theory, in that case your C vacuum and your alpha vacuum are not the same, and these two are related these oscillators are related by Bogoliubov transformations on the worldsheet, and one vacuum is a squeeze state in terms of the other. So this is
what sets the value of the angle theta, 1 minus epsilon.
Yeah.
So in other words, in your epsilon going to 0 limit,
yes.
this theta goes to 0, right?
This is a singular thing in front of it as well. So this part will be just 1. This part will be just 1.
Am I missing something? Epsilon going to
No,
0
theta goes to infinity. Tan hyperbolic of theta goes to 1.
Yeah, so here,
Okay, and
yeah.
hyperbolic goes to.
Yeah.
Okay,
So it's a
the
sign
extreme boost.
like
So
this.
is it just the extreme boost? Is it literally an extreme boost on the worldsheet?
That is precisely what it is. That is precisely what it
That's
is.
what one would have thought.
Yeah, so this is an ultra relativistic limit, which is extreme boost on the worldsheet. On the worldsheet. So all of this is being played out on the worldsheet. That's the point. Okay. So now one problem. In the sense, I don't know if you can call this a feature or a back, but what's happening is we want to look at what the physical state conditions are. And the L0 thing which you would have got just gives you level matching, that the C oscillators and C bar oscillators on this state should be equal. But now if you try to understand what n squared is, what you end up with is there are some off diagonal pieces. And n squared is an operator which you cannot diagonalize on these states. Signature of new physics, maybe?
Cannot diagonalize on the statement because of the constraints.
Yes. So this is why I again sort of I'm trying to emphasize that you should not, until unless you understand what is going on in this space-time, you should not be trying to you should be looking at only things you get from the worldsheet. Alright. So this is so one more thing is that there is again some folklore about open and closed strings being same in the tensionless limit. There's been some speculations about this by Sanoti and friends. What happens is if you look at the algebra here and you have C, so you were supposed to have a CL by 12 delta plus M0 and CM by 12.
Sorry, Arjun, another question.
Yeah, sure.
So this particular other vacuum,
Yeah.
it seems to be it's related to the boundary state that one uses.
Very good. Yes.
So you're efficiently, it seems to be, you don't want to think about space-time, but it seems to be that you're trying to take a deep rate on the space-time.
I would say that it is that. I don't know. This is the only thing that I have. So it somehow seems to be that you are moving from fundamental strings to D-branes as your fundamental objects, which so far is I don't have something more concrete to say on that, but that seems to be what is happening. Do you have something to add to that?
Just simply, I don't remember the exact expression for the D-brane boundary state.
Yeah.
But did it have an extra 1 by n compared to your equation 31?
Yeah, so so that's just down to the fact that they use A's instead of alphas out there.
Okay, so this is exactly
This is exactly that. Yeah.
So when the tan hyperbolic theta is 1, it is exactly the D-brane boundary state.
Yeah, it seems to be. It seems to be, yes.
I don't know the story. Sorry, what is the trajectory of the D-brane in space-time?
So right now, except for the fact that this looks similar to to a D-brane boundary state, I don't have anything else to.
Is it being boosted?
So this is something that I do not understand at all. I'm just saying that. So what Loga is saying is that this thing that we wrote down out here looks like a D-brane boundary state. A boundary state in the closed theory. So that's all he's trying to do.
That's not a fancy way of saying you're doing string theory in the presence of a D-brane.
No,
Yeah.
Sorry to be so poorly educated. Sorry, Loga, go ahead.
Yeah, so just usually when you say you have a boundary,
Yeah.
right? You have an let's say you have an open string boundary, the state is this,
So-
that's exactly the D-brane. It is doing in the presence of D-brane.
So the thing that I'm trying to interject out here is that we have been looking only at closed strings.
Yeah, so the funny thing is that you have closed strings, number one,
Yeah.
and you want to somehow the D-brane boundary state everywhere, which is just confusing, right? I'm not.
Yeah, it's like a space filling. This looks like a space filling D-brane because in 32
Yeah,
there is actually hidden alpha mean.
that is right. That is
So,
right. Yes.
which
Yes.
means that it's Dirichlet in
Yeah.
all new directions.
Right. Right.
Oh,
So that's
including
like
time.
that,
Including time.
Yeah, including time. It's like a D9. It's like a D9 break.
I think it's a D-1 break.
25 actually, but yeah.
Including time, no?
Including
Your
time.
It's a if you put a Dirichlet combination on every direction.
Sorry. Here is a D9. It's a D9. It's a D9.
I think it's like D-1, no?
A D-1 would be point-like in everything, no, Loga?
Yeah. So you put Dirichlet combination on all directions.
Okay.
Like you fix everything, right?
Yeah, it depends on the sign of tan hyperbolic of theta. If it is +1, then I think it's Dirichlet. If it's -1, then it's Neumann. So the difference between D9 and D-1 is that. So,
This seems to be +1.
Yeah, if I remember right, +1 is Dirichlet.
Okay.
So
It seems to be, if it were point-like in everything, you'd have to ask which point. Did you choose a particular point?
No. So, okay, so let me.
D9.
Okay, this. Okay.
it's like a space filling.
Okay. So, as I said, the mass squared is not something which is good. But one more thing that so how many minutes should I take?
Today we don't. Gautam has.
So how much do you have left?
So I could move much faster. So how long do you have? 5 minutes.
So we can go on for another 10, 15 minutes.
Let's try to wrap up within
1:10.
Yeah, let's try and do that. So let me quickly say that there's been some folklore about open and closed strings being the same in this limit. So what happens is if you are looking at the algebra and if your Cm is equal to 0, you can do an analysis of null states to show that these m's actually decouple, and you just get down to the first line. So that seemingly seems to be saying that your residual symmetries are same as an open string. So there seems to be some amount of evidence here that your closed strings and open strings are interestingly related in this list. Okay. So I'm going to say a few provocative things about applications before I end. So let's look at. So as we know, string theory has an exponential growth of states. The partition function diverges about the hydron temperature. And so what has been known since very early days is that the effective tension of strings near the hydron temperature actually goes to 0. So the analysis that we did here should be interesting, should provide a worldsheet description for physics near the hydron phase on this point. So another thing out here is that if you are looking at non-interacting strings.
What is the reason for this? It's 24.
So this one I actually don't remember, but this is reasonably.
Just because you have high values, that's it.
Yeah.
Explicitly,
I don't remember why exactly this precise form, but yeah.
The string tension is set by the confining scale, right?
Yeah.
And as they transition, confining scale goes to string values. Okay, the fact that it's of this form.
Yeah, why it's a square root and not say 3 halves or something like that is something that I don't remember offhand. But as you approach TH, it's thermodynamically more favorable to form this long string phase instead of heating up in gas or strings. So what we wanted to say is that the vacuum, this 0C that you have, is sort of a worldsheet. So this is a coherent state on the worldsheet. So it looks like something which is going to be a long string. What we want to say is that this is sort of the worldsheet analog of this emergent long string phase.
That's different from an emergent T plane.
That I mean, have, so this is something that we tried to put more thoughts on. The debrief is something more recent, so I don't really know what exactly is happening with the whole thing. But it somehow, so I mean, also the fact that if your tensionless strings become long and floppy is also extremely reminiscent of the fact that you have this emergent long string, and it seems to be that worldsheet vacuum is essentially an analog of this emergent string. So I will not go into more details of what we were trying to do in the paper, but we had some remarks on how this particular thing is a thermal object. This new vacuum should be a thermal object, and we will try to understand if it could be understood as some left-right entanglement, but which is happening again on the string worldsheet. So we had some remarks on this, and so let me skip the parts about the physics and space-time singularities, but we have some other intended applications. So what did we do? We looked at the classical strings. So what we saw is that the limiting procedure that we had followed, or reproduced earlier work by Isbell et al. So we looked at residual symmetries, central charges, looked at mode expansions, done in both the fundamental and the limiting way, and these matched well. So the methods of this residual symmetry algebra was actually central to the understanding of it. The quantum tensionless string is was more work in progress, and this is what we want to focus on. We saw that the limiting case naturally just gives you master's high spins, but fundamentally tensionless strings defined another vacuum, which was it seemed to be a squeeze state with respect to the tensile vacuum. I also briefly, yeah.
If you look at this string vacuum in the full string theory,
yeah,
it would not be a consistent state to take the string, right? Because if, for example, it would break SL2C invariance. Your vacuum is some highly Bogoliubov transformed version of the usual one, so I think it would not preserve SL2C invariance, etc. It would not be a consistent string worldsheet ground state.
That is probably not true, in the sense that I showed you this map which links these two things, right? And so the map actually seems to except for the fact that the map becomes singular in the limit, but that's something that you'd expect for all of these things, even the mapping between.
I thought the map existed if you took the usual SL2C vacuum, and then looked at the action of LNs on that and constructed states. Then you took the tensionless limit, then that map. No,
that is right. I'm just trying to say that we also linked the oscillators on the worldsheet with this Bogoliubov transformation. And there we found that since you could link it in that way, we could also find a map between these two vacuum, the thing we call 0C and the thing we call 0 alpha.
That I don't understand. Are you saying there's another vacuum you could choose for usual critical string theory and quantize the string?
So,
okay, maybe it's a D-brain, okay, that I'm willing to believe, but usually I don't think of it, usually I think of a D-brain as you put some appropriate Dirichlet boundary conditions in some
Right.
Not as a differential vacuum.
This seems to be a state more tailored to something like an upper half plane, and so on. So you wouldn't have the SL2C invariance of the usual string worldsheet, because such a state is a boundary state, no doubt.
Okay, yeah.
And this state does not have the usual SL2C.
So maybe what is happening is for finite epsilon, as long as epsilon does not go to 0, this is just a change of basis and everything goes through fine. And when you take the singular limit of epsilon goes to 0, where
your boost parameter is defined even at finite epsilon, right?
But the thing that I'm trying to say is that the algebra, and just in terms of the algebra, if you write down the algebra, it's a change of basis for epsilon, which is not 0. Only in the limit of epsilon goes to 0, you see that the extra term drops off.
Something has come up at home.
So if I understand, you had the SL to C vacuum, and then you had a boosted state, or a Bogoliubov transform state, and that Bogoliubov transformation was non-trivial for any epsilon. It became a kind of extreme transformation in epsilon went to zero.
True. Yes.
So let me look at it even before I take epsilon went to zero. Then there seems to me to be some other state other than the usual SL to C variant.
Right. But that is something that you can relate. I mean, so these will be just related by this. I mean, as I was saying, change of basis. Are you saying that? I mean,
what I'm trying to say is that if I took this state, and I then demanded. So when we normally do string quantization, we take the SL to C invariant vacuum, then we take states above it, and so on. And then you prove various nice things. Either your Lorentz invariance manifest, you prove unitarity, you do this, you do that, and so on. Now, if you start doing all of that on this other state, what I'm suggesting is that you won't get a consistent string theory.
Why not?
Okay, it could break down depending on what you want to have, and then you may not get something else. For example, if you worked in the usual conformal gauge, then what I suspect is that you are messing around with conformal invariance. So the Liouville mode decoupling may not be so clear. I'm not sure what breaks down.
The thing that I'm trying to say is that at any finite epsilon, I mean, the residual symmetry still stays the same. So it's two copies of it.
The point is that at any finite epsilon, let's say, this squeeze state can be thought of as a squeeze state. I'm sorry, this Bogoliubov transform vacuum can be thought of as a squeeze state of the usual SL to C invariant vacuum, right?
Yeah, exactly.
Okay, then we ask, is it a physical state?
It should be, yes.
Okay, so if it's a physical state, it's annihilated by all of them, and so on. Then its interpretation is that it's a state of many higher string excitations.
So I don't see why is it satisfied? It doesn't satisfy at 0 equal to 1 or ln
it should satisfy. So this particular state satisfies
physical state.
Can't have n0 equal to 1.
So the thing that I'm trying to say is that it satisfies L naught on this ground state equal to 0 and N naught on this ground state equal to 0.
So what about the original L0?
So this just means that L naught minus L naught bar on the ground state equal to 0.
These are the original left moving left and right. Okay.
So you get this.
So I'm very confused about why it satisfies this. I thought it's a state which looks like e to the alpha dagger. E to the alpha dagger squared roughly acting on the vacuum. E to the alpha dagger squared. If you just look at L0, which has a form which looks like alpha dagger alpha. It doesn't look like it annihilates it.
I mean, it will go through it.
It will go through. I see.
Because alpha on that state gives you alpha dagger.
Right.
So it looks like you get alpha dagger squared. See, this state has a form which looks like e to the alpha dagger squared given the vacuum. That's the Bogoliubov transform. L0 has a form which looks like alpha dagger. Alpha acting on e to the alpha dagger squared gives you alpha dagger because alpha acts like a d by d alpha dagger. So it seems to me like you get alpha dagger squared. I don't see why you get L0.
No, hold on. Let's do this.
Go ahead. But what happens to other LS?
Other?
LS. Is it
What
also
about the
primary?
other elements? There are a lot of constraints.
It primary also. It has to be a primary. It has to have
Correct.
equal to L.
Yeah. So the primary thing would. So what I'm trying to say is that for epsilon which is not 0. It should just be. This is just trying to change your basis, right?
For the algebra, but your state may not be. This is the question we are asking: is the new vacuum
Yes.
a physical state as per your original string theory construction?
The new constraints, right? The constraints are different. So why would it satisfy?
See, because your states in the original Hilbert space in which were unphysical.
Sure.
One of those.
Sure. No, I would say that it's not that, but let me try and argue my.
I mean, we can do it after the talk. You don't have to. You don't have to do it.
The problem here is alpha themselves do not commute with the constraints, the LS.
Yeah.
Right? They don't. Because they satisfy some, because they give you some other
so yeah, one thing that I agree that it's the primary constraint will not be. I mean that will not go through. That is right. So it will not be a primary anymore because you have L. So
but if it's not a primary, it's not a
yeah.
physical state. No, I mean this is a
I don't think you see why the L0, can I say L0 is like, if you just think of it like,
Yeah.
L0 is like the worldsheet Hamiltonian, right? This is like a state which is seen by a Ringler also. So generally the Minkowski energy for a Ringler state is infinite.
Yeah, so you are, I guess, right, because what's happening
is
is,
Minkowski energy, so it doesn't have L0 equal to 0. I know there's some wrong signs and so on, there's an x0, so that's why I'm not sure, but apart from that, it wouldn't like.
Yeah, actually that's a good way to put it. The Ringler vacuum has a diverging stress energy at the horizon and so on. So how would it meet just expectation value of T alpha beta equal to 0? It can't meet that. Yeah, in fact it can't meet that. Look, it can't be a primary because...
No, it is not. That is right.
Yeah.
Because, this equal to 0 would mean that this, Ln minus L bar of minus n of capping of this equal to 0. So since it's a mixture of these things, it will not be.
That's already not physical. I don't see how it satisfies the L0 one also. That's what I'm confused about. Because it doesn't satisfy even...
No, for the L0 bit, this guy is 0, right?
But even then, because of just looking at the state, I'm confused about how. Okay, but you say it works out.
Yeah.
Okay, but look, I think we all agree.
Yeah.
It's not a physical state in terms of the original string. They usually require it to be a primary.
Okay. This is something that I could get back to you guys on if I had. So what I was trying to say is that at least for the L naught and M naught constraints, things do go through. But in the limit where we're looking at the actual tensionless case, this map is a singular map essentially.
I mean, you could be saying that for epsilon equal to 0, this is okay. For a general epsilon, it seems to me that at least if I thought about the full string theory, then this state, your Bogoliubov transform state, is not a physical state.
So let's try and so the thing that I'm trying to say out here, so the map that we were trying to make was trying to see that if this if this were a state in the original theory, it would be a highly excited state.
Highly excited is not something you see here. No, it's something.
The constraints we get from living G alpha beta tell you that T alpha beta vanishes weakly, which means expectation value of T alpha beta goes to 0. Right? But in this state, expectation value of T alpha beta cannot go to 0 because, as Surat was saying, it's like a Ringler vacuum.
True. So, as I was saying, what we are doing in this particular case is that when we look at the fundamentally tensionless objects, so in that particular case, we proceeded in the usual way. We quantized the theory, and we had these C-seated operators, and we are trying to build a Hilbert space from this. So that's something that you can obviously do. All I'm trying to say is that the vacuum that you had earlier in terms of the alpha oscillators and the vacuum that you have in terms of the C oscillators are not the same. So one is, if you write it in terms of these Bogoliubov transformations on the worldsheet, in that case, this C vacuum looks to be a squeeze state in terms of your alpha vacuum. And the fact is that in that particular case, since it's a squeeze state, it would be a highly energetic state. If you are sitting at the alpha vacuum, this would look like a highly energetic state. That is the claim that I'm trying to make.
What do you mean energetic? It's not energetic. It still says L0 is 0. It just has a lot of oscillators and has an equivalent minus k square. Energetic in space-time.
Yeah.
Energetic in space-time.
Yes. So that's the claim, and I see your point about the fact that this may not be a proper state to look at in the in the original alpha IITK space. But that's something that it's not a problem per se, but it's something that I guess we should be a little more clear on. But okay, so let's just wrap up. We also did a supersymmetric version of this and similar things to go through. And so I had a few more things to say, but I think I'm rapidly out of time. So one of those things is what happens to space-time. And so let me just mention this. So this is a weird limit, so we'd expect something very drastic to be happening on the background as well. And this may be a deformation of Minkowski space-time. The way we want to understand this is by implementing a Galilean conformal analog or the vanishing of the beta functions for maintaining conformal invariance on the worldsheet. So this is some work which is underway, and we're also looking at other things about links to higher order physics and connections to higher spins and also parallelography, and also trying to the aim is also to try and make up the loss mandating from the point of view of the worldsheet, but we're still far away from that. We could perhaps be trying to take a tensionless limit on which was written, and I think I have bored you guys enough, so I'm going to stop now. Thank you all for your attention.
I think ICTS gets first dibs on questions.
Yeah.
Excluding Subrat, who's today TIF. Go ahead, Loga and friends.
Yes, so I think, my worry is still that, if you had a basic growth diagram of this particular thing that we are discussing,
Yeah.
that the errors don't kill it,
Yeah.
will show up as a statement that the BRST charge would not kill it.
No, so that's a valid thing to ask, I guess.
And that's one thing, and there's also another direction which you are worried about, which is that usually in the usual string theory, we also take the single gauge management, which is the 0 1 or the B field kills it, which also I'm worried about how I'm going to do. But the point here is that, this all these other interpretations of the space-time and so on,
Yeah.
I think are very, very problematic because of the fact that the BRFT is not realized in this C vacuum very well, I think.
What I'm trying to say, Loga, is that it may not be that you use the BC ghost system, but you use something which is which is suitably modified form of the BC ghost system. And I think one should be able to devise a way in which you also address this. And since I don't have the math done right now, I can't say for sure, obviously, but I am reasonably sure that it should go through with some amount of modifications, but I hope to be able to report on this later.
Yeah, just to add to that, if you started with the action that looked like V alpha, V beta, del alpha, del beta, del alpha x, del beta x, that action itself has some gauge symmetries, and you could quantize that action to a Fali-Popper quantization.
That's right.
That would probably give you perhaps this.
Yeah.
And then there would be that would probably, there's probably some constraint quantization of this, and maybe you get some constraints or not if you do the about critical dimension or whatever. You say it's not. But maybe what's open is the relation of that theory to the original string theory that you started.
Yeah, so
these questions about whether the state was physical or would come about if you try to make a relation between those theories.
Yeah, okay.
There is some quantization of that action which is presumably consistent.
So one thing that I can say right away is that while we are trying to do the supersymmetric version, it seems clearly that the mapping between these two vacua are such that your level matching itself also breaks down. So in a sense, the thing that you guys are saying probably makes sense. I was a little perturbed about the fact that this is not matching, but probably that is what one should be expecting. So
it's some theory.
Yeah, it is.
Okay, but maybe you shouldn't even think about it in the original. In terms of the original.
Yeah.
Maybe it's.
It's probably good to as long as you're not imposing the physical state state conditions of your usual string theory on the Hilbert space. It's a state there.
One thing I didn't understand, what was the space-time spectrum you got at the end of it? You mentioned this.
Okay,
what is the space-time structure that's
one thing is that that when we were just looking at imposing the tensionless constraints on the tensile Hilbert space,
Everything is sense.
yeah, I mean everything just, I mean,
You
gives
have
you,
infinite states at zero mass.
yes,
Yeah, but that's a different theory from the other.
that is right, that is right. So what
What is it? Sorry, what is
so he's just saying that, I mean, this theory is not the same as the other one.
No, in this theory, what is the spectrum in space-time?
So this theory, the spectrum in space-time, so I showed you that the L, I mean, this L not constraint goes through. From the M not constraint, you do not get a mass. I mean, your mass is off diagonal. So your mass is not a very physical thing here at all. So this is something that we do not understand so well. What I'm trying to say out here is that since these are very different sort of objects, it might be that the mass squared operator doesn't make sense.
What about m squared equal to 0? That state also doesn't satisfy.
M squared equal to 0 would be fine. I mean, there'll be certain.
Which have m squared equal to 0.
Okay, hold on. So what happens is.
So maybe you just look at m squared equal to 0, which is what we expect anyway.
Okay, so what happens is here. So you see you get some off diagonal pieces here.
So let's say I just wanted to look at m squared equal to 0. Does that satisfy the constraint?
M squared equal to 0. I mean,
probably all CMs are 0. So
Yeah.
no excitation. So
yeah.
So that satisfies the constraint.
That I think should be fine.
So
Yes.
then why isn't that your spectrum? That's your spectrum. It satisfies the constraint. Satisfies
No, I mean, the thing that I'm
And that's what we
trying to say
expect
is that,
anyway.
I mean, you probably need to define some other, observable here.
No, but didn't we anyway expect to get only m squared equal to 0? We only expected to get m squared equal to 0. So why are you happy that you get m squared equal to 0?
No, I mean, I'm saying that, yeah, so what you have is if you act your states, so act your C oscillators on it, it gives you something which is weird, right?
So you don't have your C oscillators on it. No, you're looking at the states with satisfied constraints. So you have these constraints and you ask what are the values that m squared will satisfy ln and mn equal to 0.
So you're saying that I should just be happy with that. I was trying to think of this as a ground state, and I was trying to think of, yeah, I mean, the Hilbert spacing bit of.
will satisfy m squared equal to 0, of course, right? Or
So
you're
what?
saying only one state
Yeah,
will
yeah,
satisfy.
that is. So this is something that I've not exactly, I mean, given much
because there
thought
probably
to.
is some sign in the oscillators, no? So maybe there's a sign. in
No,
the
there's no sign here.
There's also a 0 mode contribution. Where is that?
Zero mode
I
contribution.
mean, usually you get L0 equal to 0 because there's 0 mode contribution which cancels.
Yeah, sure. So you have the whole thing. You bring it to one side and then you get what mass square equal to this is. So this is, yeah, I mean, m not acting on this state psi equal to 0.
So it sets all oscillators to be 0.
Yeah, so that I think, so I mean, my interpretation of this is just that, I mean, since it seems to be a sort of non-perturbative state or something, mass squared may not be the best observable on it.
And you don't have a sign for sure for the oscillators that are tied there.
Yeah.
No, there's no sign. It really adds. Okay.
Yeah, this, but I mean, the thing that I was trying to do is, I mean, I was just trying to say that this is just weird, and we might have to, I mean, rethink this in something.
In view of the hour, if it's okay, unless ICTS has
Severe objections.
has additional pressing questions, we should take them. Then maybe we can. The rest of us here can talk over lunch. ICTS, any more questions or comments?
Okay.
Okay,
Thanks, guys.
Thank you. Thank Arjun again.